So today I will discuss a specific problem that I haven't touched so far. It's the stability of kinks and more specifically in nonlinear Klein-Gordon equations. And this is following a recent work together with Fabio Pusateri, who's in Toronto. So as usual, some of the stuff that I will discuss is specific to this problem. So not only kinks, but also the fact that we are dealing with a nonlinear Klein-Gordon equation. But many of the ideas and many of the tools are relevant in much greater generality. And as often in PDE, rather than trying to elaborate a global theory that becomes so full of particular cases that it's not understandable, it's better to just deal with a particular case with the understanding that much can be adapted to other situations. So kinks, what is a kink? A kink is a stationary solution that looks like that. So this is k of x as a function of x. And so the difference with what we've been doing so far is that it has this non-trivial limit as infinity. It's not a localized state like all the solitons we've discussed so far. And this leads to all sorts of interesting questions. And also physicists are very fond of this sort of objects, which are termed topological solitons. So of course in 1D there is not much topology. There is this so the topology, if you want, is the non-trivial constraint at infinity. That the kink has a non-trivial has a different limit at plus and minus infinity. So it's not really topological. In higher dimension, there are similar objects that indeed have more topology in them. But you see, since this kink has a non-trivial limit at plus and minus infinity, new questions will arise compared to what we've done so far. Right? So far, we've been looking at solitons that decay and that are localized. Okay, so the general form of the equation is the following. Plus u prime of phi. So U is the potential energy. Oh, and sorry, Clemens, if you could turn off your microphone. Thank you. So U is the energy, and this is the usual wave equation. So this equation derives from the Hamiltonian. Whoops. And the fact that there is such solutions as this kink is linked to the fact that the energy U will be assumed to have a double well form. So that's U of x as a function of x.
Pierre, question?
Yes.
Could you have kinks in a nonlinear Schrodinger, or it's just specific to wave equations?
Yes, it's in general in nonlinear Schrödinger equations it's called in the jargon it's called dark solitons.
Okay.
Because in optics, in optics, if you have a soliton like this one, there's going to be a bright spot where the wave function is not zero, and otherwise it's going to be dark. But for a solution such as this one, it's the opposite. It's going to be dark close to the origin and bright everywhere else. Yes, and then there are a few differences, but essentially, the same sort of structure appears for nonlinear Schrödinger equations. Right. So as I was telling you, there are kinks that look like, say the two minima are -1 and 1, and there are kinks that connect these two minima. This is -1. This is 1. And in terms of the ODE, so the ODE that a kink satisfies is the following. So the ODE is minus psi double prime plus u of psi equals 0. And so the phase diagram is as follows. So this is psi, this is psi prime. There are, two fixed points which are the minima, 1, -1, of the energy, and then which something like that. I hope you get an idea of the phase space diagram, and you see there are two heteroclinic orbits. This one and this one. Heteroclinic. And these two heteroclinic orbits correspond to the kink and minus the kink. Right. I should say I will assume that u is always even. And the kink is always odd. Why that matters will soon become clear. Okay, so for this sort of objects, you want to ask the same question. Are they stable? In which sense are they stable? So just like for KdV or NLS, orbital stability is rather easy to prove, and indeed it was done in the 80s. I forgot who did it. The next question is that of asymptotic stability. So as far as asymptotic stability, there is an important work by let me remember, Martel, Munoz, and Kowalczyk, who proved local asymptotic stability. What that means is that if you stare at a compact region, on this compact region, the perturbation away from the kink will go to 0 as time goes to infinity. So that's a very important progress on this question. But it has some drawbacks. It's the decay you get is not optimal, and it's only a local statement. So what we tried to do together with Fabio was to get a global statement, and this we could do under some additional assumptions on the potential and the kink, which I will mention in due time. And I should mention there is also a recent work of Delors and Masmoudi on this question. And there is also a series of work by Luhrmann, Sog, and Soffer and Sog. Which. Okay, so there has been a lot of work recently on this question. Essentially, depending on the potential, you can prove global asymptotic stability or not, and in some cases, it seems very, very difficult to get the full picture. Okay, any questions?
Yeah. Yes, it was about VOD. You have. I don't get why there isn't a prime on the U.
Oh yes, there is a prime on the U. Thank you.
Okay.
Okay, so let me erase that. Okay, so what are some, particularly interesting models? So examples. So essentially the freedom you have is in choosing the potential. So, many details of the dynamics actually depend on the potential. Of course, stability or not, but what physicists are most interested in, at least if you look up the literature, is the question of collision of kinks. So you take one kink and one anti-kink, so one that goes up, one that goes down. You can give them some non-zero velocity by using Lorentz invariance. And then you let these objects collide and you see what comes out of the collision. And then there is a whole zoology. Mathematically, it's very hard to understand, this collision problem, essentially because you leave the realm of perturbation. And as you know, in analysis, if you don't have explicit solution or perturbative approach, there is not much you can do. So it seems very hard to attack the question of the collision of kinks. And even more so because if you want to understand the collision of kinks, the very first thing you need to do is to understand the stability of one kink. And this is, not yet perfectly understood. So I got a bit carried away. I was about to tell you about examples. So there is the most famous model is called the 5-4 model, and it corresponds to a Ginzburg-Landau potential, which is 1 minus phi squared. Well, it's a bit the first one, you know, you're tempted to write. Then there is the choice u of phi equals cosine phi. And then, of course, you don't have only two wells. You have, you know, periodic function that has an infinite number of wells. And this is called the Sine-Gordon equation. And it's also very famous, in particular, because it is completely integrable. And there is a whole, you know, set of methods coming from complete integrability that you can apply to this specific case. And then pretty much you're free to choose u of phi as you want. And you know, there is the so-called phi 6, which is phi squared times 1 minus phi squared squared. There is the double sign, which is alpha cosine plus beta cosine phi over 2. And I don't think they have any, you know, there's a particularly good reason for this specific formulas, as far as I can tell. You know, it was just physicists trying to understand how the potential has an effect on the dynamics of the problem. Okay, I should say these equations, so recall the equation we're talking about is dt squared phi. And it's a nonlinear wave equation in the end, so there are the classical symmetries. Of course, space translation, this equation is invariant by space translation. So if you take phi of tx and you map it to phi of tx plus x naught, well, you know, this leaves the set of solutions invariant. More interesting, there is the Lorentz symmetry. In particular, the Lorentz boosts, which are given by the following transformation. Take phi of tx, and you map it to phi of x. Where v is less than 1. So you see, you can apply these two symmetries to kinks. Well, if you apply the first symmetry to kinks, you just, you know, translate the kink, so it's not very interesting. If you apply the second symmetry to kinks, then you see that the kinks, well, they change their shape a little bit, and they start moving at a certain velocity v. This is how you can get kinks to collide. But for us, we're going to get rid of symmetries. By assuming that phi is odd. So the kink is odd, phi is odd, and if the data is odd, the solution remains odd. So this is preserved by the nonlinear dynamics, and this cancels these two possibilities. So if you want the only soliton that is compatible with oddness is the kink itself. Applying these symmetries to the kink destroys oddness. Okay, so this will simplify a little bit the discussion because, well, this will simplify the discussion. Okay. So as we saw when dealing with NLS type equations or KdV type equations, understanding the linearization around the soliton is crucial. So the linearization if you linearize around the soliton, it's not hard to see that the equation you get is dt squared minus dx squared plus u double prime of psi applied to v equals 0. So this is the kink. Maybe I should have called it k. And this is the perturbation. Okay, and so obviously to understand this equation, you need to understand the Schrödinger operator h, which is minus dx squared plus u double prime of phi. But since phi has a non-zero limit at plus minus infinity, and u double prime does not vanish a priori, this becomes minus dx squared plus v plus m squared. So this is just a real number, and this is a Schwartz class potential. So now this looks more like a Klein-Gordon equation, right? Minus dx squared plus m squared, that's the Klein-Gordon, and you add a potential which is rapidly decaying. So what can we say about this Schrödinger operator? Well, of course, the continuous spectrum is well, m squared infinity. Since you're adding m squared, the role of the zero, maybe I should call. It's really this is really h. This makes more sense. So this is not h. So if I look at h, it has continuous spectrum 0 infinity. At energy 0, as we saw, it makes a big difference whether there is a resonance or not. So resonance at 0. So it depends on the model. For the phi-4 and for the sine-Gordon models, there is a resonance at 0, but there is no resonance at 0 for, in general, or I should rather say, generically, there is no resonance at 0 because, as we saw, resonances are unstable, and so in a sense, if you choose u at random with probability 1, there is no resonance at 0. But as I was saying, for the two most popular models, the phi-4 model and the sine-Gordon, there is a resonance. So, sometimes life is tough. And finally, so there might be so there are eigenvalues that are related to symmetries, but these we cancelled through the oddness assumptions. And then there are eigenvalues. So in other words, these eigenvalues related to symmetries are always associated to even eigenfunctions. So under the oddness assumption, you get rid of that. And what I wanted to say, yes, there are also other eigenvalues that are not related to symmetries and that are known as internal modes.
Sorry, just I was wondering about the oddness assumptions. Does it mean that also the perturbations are assumed to be odd?
Yes.
Okay.
So same thing. Internal modes, it's model dependent. Once again, the phi-4 model has internal modes, by which I mean eigenvalues not related to symmetries. So the phi-4 model has internal modes, but some other potentials don't. So the theorem we proved is the following. If, well, first, there is no resonance at 0 energy, and second, there are no internal modes, then V, so not for the linearized problem, but for the full problem, V goes to 0 as t goes to infinity, and there is this, the usual scattering with correction. There is this logarithmic correction in the phase. So example, so for instance, this applies to the double sign potential. So U equals alpha cosine phi plus beta sine phi over 2. Of course, the problem is that it can be tricky to check these two spectral assumptions, because sometimes it's hard to solve explicitly spectral problems. But for this model, the assumptions are checked for some region in alpha beta, so a certain open region in alpha beta under which these assumptions are checked. So, on the one hand, that's a nice theorem because it's the first of its kind that gets global asymptotic stability for this sort of model. On the other hand, the assumptions leave out, the two most interesting, or at least best known cases, which are the phi-4 and the Sine-Gordon models. And for these, the difficulties that arise, seem very, very serious, and I have no clue how to deal with them. Okay, so during the rest of this lecture, I will try to give you an idea of how to attack this problem. So essentially, the same ideas as what we've seen so far apply, but there is an additional difficulty which is related to this non-trivial behavior of the kink at infinity, and we'll see how to get around it. Any questions?
Just because we have, if the derivative in time is of order 2, we have to consider vector valued operators, or like, do we need to consider V and its times derivative when we are doing the computations?
Yes, so that's a very good question. You can combine V and its time derivative into a complex valued unknown function. So the problem remains scalar, and we'll see, more specifically how to do that in 20 minutes, I'd say.
Okay, thank you.
Okay, so let's erase. Okay, so as usual, we're going to, I know, this is no good. This is good. So we write phi as a psi plus v, where this is the kink, this is the perturbation, and we expand the solution in V, or rather the nonlinearity in V. And so what you obtain is dt squared V. So the equation satisfied by V, the perturbation, is for the linear part, we already wrote it. That's the linear part. And then you get nonlinear terms. Sorry, AV squared plus A plus B V cubed, etc. So here V, we saw that it's a localized potential. And this corresponds to u double prime of psi minus m squared. M squared is the limit of u double prime of psi at plus minus infinity. A is u triple prime of psi, and B is u differentiated 4 times of psi. So this one looks like that. It's not the kink, but it looks like that. And B right, and B looks something like that. Okay, so compared to what we've been doing so far, you see there are quadratic terms here here there are quadratic terms that we don't really know how to deal with because they decay very slowly. The decay rate is the same as for Schrödinger, it's t to the minus a half. And there is A, which itself does not decay in space, right? So we cannot hope to make use of something like improved local decay. Then the cubic terms, they can be treated in a way which is very reminiscent of what we did for Schrödinger, but quadratic terms, it's another story. So in order to treat these quadratic terms, the key is to use normal forms, which I am now going to explain. So, in terms of this oscillatory integral that we've often written, it's a specific way of approaching this oscillatory integral in order to take advantage of time oscillations. So that's, maybe the best way to see normal forms in this specific context. But normal forms are, very important method in the theory of dynamical systems. And so I'm going to explain a little bit, what they mean in finite dimension, and then what happens in the case of a flat Klein-Gordon in the absence of a potential, and finally, how to use normal forms in the presence of a potential. Okay, so normal forms, first installment, which is, finite dimensional. And of course, this goes back to Poincaré. Who got interested in these questions in the framework of celestial mechanics. Right. So, for the sake of concreteness, let's look at a model system. U dot equals U v squared, IV dot equals, V dot lambda V plus U squared. Okay, so of course V squared and U squared, you can think of them as just, the beginning of the expansion of a more general nonlinear function. There is U and V are scalar valued functions. And obviously, UV equals 0, 0 is an equilibrium. Okay, so the question that you'd like to answer is how stable how stable is this equilibrium? And of course, this becomes more interesting if you have more complicated systems, but this will be easier to do computations and explain what's going on. How stable is this equilibrium? So, the most naive answer is to say, okay, let's consider a perturbation UV to be O of epsilon at time 0. So, in other words, you perturb the equilibrium by something of the order epsilon. Then what you see is that IU dot, so heuristically speaking, IU dot equals U plus O of epsilon squared. IV dot equals V plus O of epsilon squared. So the time it will take for this perturbation of size epsilon squared to have an influence on U and to change U by more than epsilon is 1 over epsilon, right? So if I wait for a time t, these things accumulate and they give t times epsilon squared. And this means that U dot can change by, can change by at most t times epsilon squared. So on 0t, UV change by epsilon squared capital T. Ouch, this got cut. Epsilon squared capital T. So in order for this to be less than epsilon, I need T to be less than 1 over epsilon. So if T is less than 1 over epsilon, U and V remain of size epsilon. Okay, so by this very naive computation, what you get is that if you have a quadratic nonlinearity, the time at which you're stable is like 1 over epsilon, with epsilon the size of the initial perturbation. Okay? So of course, if instead of the quadratic nonlinearity I had a cubic nonlinearity, the time of stability I would get would be much larger. It would be 1 over epsilon squared. right? Because instead of O of epsilon squared, I would get O of epsilon cubed, so one order smaller. So for this reason, it's interesting to find a transformation that increases the order of the nonlinearity, because it will mean that this system is sort of one rank more stable. Was this explanation convincing? Do you have questions? Okay, so if you're convinced, we can try to find a change of coordinates. So you set capital U equals little u plus alpha v squared, and capital V equals little v plus beta u squared. Okay, so if I want it to be completely general, I should put any quadratic expression in u and v, but given this specific model, this will be enough. Okay, so you take this new unknowns. You express little u in terms of capital U. You plug that in the model system, and what you see is that new equation. For instance, if I look at the equation on capital U, I get IU dot equals capital U plus right, 1, so it's a small computation, minus 2 alpha lambda plus alpha times v squared plus O of u cubed. And similarly for the equation on capital V. So if I choose alpha such that this is 0, then the equation becomes cubic to the next order, right? Because you cancel the quadratic term and it's cubic. And furthermore, this is possible if, so what you need 1 minus 2 lambda non-zero. And this is a non-resonance condition. Okay, so of course, once you obtained cubic terms, you can apply once again this transformation and keep on going until you hit resonances. As long as there are no resonances, you can iterate this transformation. Okay. So now the idea is to apply this sort of ideas to nonlinear dispersive equations, nonlinear wave equations. Much remains the same. The difference, of course, is that the system is not finite dimensional anymore. It's infinite dimensional. And the other difference is that, once you manage to increase the degree of the nonlinearity enough, you can just integrate it out because waves are decaying. So once the power is big enough, the nonlinearity becomes integrable in time, and you're good. Okay, so the next step is to try to apply this to nonlinear wave equations. Do you have questions? Is it? I mean, I was fast, so be it at the technical level or at the philosophical level, you might have questions. Please ask.
Just in this case, it helps to keep U small, but it isn't enough to prove the asymptotic stability. There needs to be some other arguments, like to begin.
Yes, that's right. Yeah, that's a very good point. Using these methods, you cannot really get global stability, but you can get stability over very long time intervals. So typically, if there are no resonances, and if you iterate, so you need a Diophantine condition on the frequencies lambda here. So if you have such a Diophantine condition, and if you iterate this sort of construction, you can get stability up to a time like exponential 1 over epsilon. And this goes by the name of, I forget, a Russian mathematician. Right, but so this sort of dynamical systems, they can take an awfully long time to become unstable, and something bad might happen.
Okay, thank you.
It's like the solar system. From what I understand, there is no reason to believe that it's eternally stable. Maybe at one point, small perturbations will build up, and for instance, one planet could be expelled out of the solar system. So hopefully not Earth anytime soon. But these sort of things are very, very difficult to understand.
So is it the Lyapunov stability?
No, it's not Lyapunov. It's let me find it. I'm blanking. Okay, so let's erase. Okay, so normal forms too. Let's look at the nonlinear Gordon equation in the case of a zero potential. And this is due to Jalal Shatar in the 80s. So let's look at this problem. So for the moment, I leave the dimension unspecified. And so what you can do is you can define V. So this will answer the question of Paul, I believe. you can define V to be dt minus I. To make the problem first order. So V is now a complex valued function, but it satisfies a first order in time equation, as opposed to U, which is real valued but satisfies a second order in time equation. So the equation satisfied by V, if you do the computation, where dx is defined to be square root of 1 minus dx squared, or in other words, it's the Fourier multiplier and this I denote bracket xi. Okay, so you can recast the equation under this form, and then as we've been doing often, we'd like to write this as an oscillatory integral. So we set f equals e to the minus itxc v, and then the equation satisfied by f is the following: f hat of txc. So, you know, it's the manipulation we did often. Okay, so here there is the phase function. So there are many possible wave interactions. You see, on the right-hand side, you have VV giving V, VV bar giving V, or V bar giving V. So each of these interactions will lead to a different sign. I will explain that soon.
Just the division by the bracket of the partial derivative is defined in Fourier space.
Same thing.
Okay,
Yeah.
Okay, thank you.
Right. So then you have f hat.
And what is V bar?
V bar is the complex conjugate of V.
Oh, okay.
Right, so f hat of xi minus eta, f hat of eta divided by eta xi minus eta. So sometimes the f hats carry a bar, but I'm not writing them. And this phi, it's actually depending on two indices. And it gives xi. And actually, here you're summing over all possible signs. Okay, so it's the classical expression we've been writing, a few times. And the critical thing for nonlinear Klein-Gordon is that observation for any choice of the sign and xi and eta, this phase is never 0. So in other words, there are no quadratic resonances in the problem. So that was the fundamental observation. So then you can apply, normal form transformation to turn the problem into cubic. So problem becomes cubic. And then, in dimension 3, that was the case originally considered by Chatin. Once the equation is cubic, you can just use decay to swallow up the nonlinearity. In dimension 1, you're back to a cubic problem in 1D, which is something we saw in the context of NLS, and here you can apply similar methods.
Sorry, I have a question.
Of course.
To the denominator in the equation in the third row, where we have this bracket of one.
Yeah.
Actually, what exactly does it mean? It's an operator acting on V normally, but here it's just in the denominator without any V. I don't know what it means exactly.
Yes. So by convention, F over dx hat is F hat of xi over xi.
Okay. Thank you.
Thank you. Any other questions?
I have a short question. Namely, you wrote that becomes cubic in D equals 3 and 1. So is there any reason why you didn't include 2?
Oh, so these are the two extreme cases. In dimension 3, the decay is so strong that once it's cubic, it's good. And in dimension 1, the decay is weakest, so you get this correction to scattering. Dimension 2 is sort of in between.
Okay, so it's even easier.
Yes. So yeah, I mean, it is certainly easier. I forget the details, and I'm not sure who did it. So dimension 3 is Chata. Dimension 1, there is Delors and Hayashi and Naumkin. Maybe some others, but at least these. Okay. Any other questions? Right, so here's maybe another way of looking at these normal forms in the context of nonlinear partial differential equations. So if you look at f hat of txi equals f hat naught plus eis phi f hat of eta f hat of xi minus eta d eta ds, and I'm omitting some details. What you can do is integrate by parts in S using the identity So you plug this in the integral, and you integrate by parts. And what you get is the following. So first, there are boundary terms that have to do with the fact that this integral has bounds, and you get EIT phi divided by phi f hat of eta. I omit a few constants and signs, and this is always depending on S. So that's the boundary term. There is another boundary term at time 0. And then there is an integrated term where you get ds f hat. And you see that this transformation, so this simple integration by parts, corresponds exactly to the normal form transformation. Namely, this is the quadratic correction. And this is the cubic term. Because the time derivative of f is quadratic in f. So that's another way to put it. So you see this is quadratic, but now there is no time integral, so this is better. And there is a time integral here, but this term is cubic, so it's decaying faster.
Sorry, I have a very short question about the quadratic term. So you wrote the ds. Is this just supposed not to be there? Because you said there is no time integral in the quadratic term.
Right. This term, there is no IDS. Yes. Thank you.
Okay.
Thanks. Right. So this corresponds to in the normal form, the presentation I gave for the normal form transformation. This corresponds to the quadratic correction. You add to u, and this is the cubic term once you did this correction. Okay. So now, last step: how do we implement this sort of ideas for the kink, or in other words, for nonlinear Klein-Gordon with a potential? Oh, sorry. Can you repeat?
I have a question on the cubic term, whether there's still some 1/5 or so.
Yes, there is if I did not write it down, there should have been a 1/5. Yeah.
Okay.
Okay, so normal form 3, back to the kink. So then what you have is And well, we're going to apply the same idea by defining h to be square root of minus dx squared. Sorry, h is r minus dx squared plus v. And then, using the same sort of functional calculus, if we said v equals dt then the equation it satisfies is I dt v minus okay, and same thing as usual, we define f e minus it root h plus 1 v. So each time there is an expression involving h, you define it by the usual functional calculus, and then f hat of t. Then we switch to the distorted Fourier transform. So now we are back to a question that we asked earlier. What does this equation mean on the distorted Fourier side? So first, frequencies don't have to add up to 0. So now the phase involves 3 frequencies that do not have to add up to 0. And then you have f tilde of eta, f tilde of sigma, divided by eta sigma, and then you have this distribution mu okay. And now there are 2 cases to consider. First, on the singular support of mu. So remember, the singular support of mu is very similar to what happens in the flat case. Frequencies have to add up to 0, modulo sines. So on the singular support of mu, the phase is never 0, as we saw in the flat case. So you can turn the expression into cubic. So that's on the singular support of u and in the neighborhood of it. So you can cut off in eta and sigma to restrict to a place where phi does not vanish, and then you do a normal form transform. Now, on the rest of the support of mu, phi might vanish. Phi might vanish. So that's annoying. And what's even more annoying is if the phase phi is also stationary with respect to the other integration variables, eta and sigma. So what's worst is if phi equals d eta phi equals d sigma phi equals 0. And if you do the computation, this happens for eta equals sigma equals 0 and xi equals plus minus root 3. So it's a very simple computation. So in this set, it looks like we're screwed. But the redeeming feature comes from improved local decay. How can you read off improved local decay on this expression? Well, this simply means that mu will actually vanish if eta or sigma is 0. So this is the translation on the Fourier side of improved local decay. So this gives a cancellation that will get rid of this worst possible interaction. And this is why we need that there be no resonance. We need that the potential is generic, because then you get this improved local decay, which gives the key cancellation for this problem. Okay, so that's the very basic ideas that go into the proof. Maybe you have some questions. I would like to just give some more general perspectives afterwards. But on this more technical aspects, do you have any questions?
Yes, I have a question. So the previous result you mentioned was on every compact, the solution goes to 0. That
Yes.
was the...
Yes.
Now,
Yes.
what your statement is that it's uniform with respect to the compact. So in other words, it goes to 0 uniformly.
That's right.
the...
That's right. And sorry.
We expect the sum. Yeah.
And not only that, but the result of Kowalczyk-Martel-Munoz also doesn't have a decay rate.
Oh, and you do have one.
And here we get the optimal one. We get that globally it decays like 1/√t. What they get is that on any compact it goes to 0. And I expect that in some other problems, this global information is actually crucial, in particular for quasi-linear problems.
For many linear problems. Yeah. Okay, thanks. Mm-hmm.
Okay, so let me erase that. All right, so let me, to conclude, mention some perspectives. So, yeah, what I would like to stress is that, this domain of mathematics, of nonlinear analysis, this field is really full of open questions, and even, the most basic open questions are mostly unanswered, or the most natural questions are unanswered. So, stability of solitons in most